All right, let's pick back up right from where we were cut off. So we were talking about electron density and the fact that in an HCl molecule, we have covalent bonding and we have uneven sharing between the hydrogens and the chlorines. So our electron density is more in the chlorine end than the hydrogen end, making the chlorine a little bit more negative than the hydrogen. So we can consider this to have consider it to be like an increase in electron density for the chlorine, which is very similar to reduction if we're defining reduction as gaining electrons. And a decrease in electron density would be considered oxidation. All right. Our most common definitions of oxidation and reduction have to do with gaining and losing electrons. Note that in oxidation and reduction, the two processes are always paired. You can't have oxidation without reduction, and you can't have reduction without oxidation, because the electrons have to come from and have to go somewhere. Okay, so if you have an atom that loses electrons, that atom is being oxidized. If you have an atom that is gaining electrons, that atom is being reduced. And we use the little set of terms, Leo and Ger, as like a memory tool to help us, to remind us which is which. So Leo stands for lose electrons, oxidation. Ger stands for gain electrons, reduced, or reduction. And that's one way to help remember it. So you see down here with this example of sodium and chlorine, you have solid sodium plus chlorine gas, giving us NaCl salt. The sodium goes from solid form to a sodium +1 ion. Obviously, if it's going from neutral to positive, it's losing an electron. That's oxidation. Chlorine gains 2 electrons and becomes an anion, well, 2 anions. That's reduction. Okay? Another way that we can determine the direction of electron flow is using oxidation states. Oxidation states look very similar to charges on ions, but they are not the same thing. Oxidation states are these imaginary numbers that we use that helps us keep track of where our electrons are moving to and from in a redox reaction, but they're not an actual charge. A charge, on the other hand, is something real. It's something that we can measure. All right. So let's look at this example here. We have carbon plus 2 sulfurs gives us carbon disulfide. Now, we haven't gone over assigning oxidation states yet, so you'll have to believe me that these are the oxidation states of these components. Carbon starts at an oxidation state of 0, so does sulfur. In carbon disulfide, the carbon changes to an oxidation state of +4. The sulfur changes to an oxidation state of -2. All right, so our carbon's going from 0 to +4. That's an increase in oxidation state. That is another definition of oxidation. The sulfur goes from 0 to -2. That is a decrease in oxidation state, which is another definition of reduction. So you have to be familiar with both definitions of oxidation and reduction. Oxidation means losing electrons, but it also means an increase in oxidation state. Reduction means gaining electrons, but it also means a decrease in oxidation state. Okay. So here are the rules that we are going to use to assign oxidation states. We have to follow this set of rules in order when we're assigning oxidation states. All right. When we say that these are in order of priority, that means that rule 1 has to be followed first, then rule 2. If any 2 rules come into conflict, the rule with the lower number takes precedence. So, rule 1 is the most important rule, then rule 2, then rule 3, etc. So rule 1 is that free elements are always going to have an oxidation state of 0. So you see that these elements are in their natural form, okay? Or they're free elements. That's the term that we're using here. So sodium exists as Na in nature. Chlorine, a diatomic element. I know some of you guys need a reminder as to what that is, so make sure you know. A diatomic element exists as a molecule in nature. So Cl2 is chlorine in its elemental form. So both of these have an oxidation state of 0. Monoatomic ions, on the other hand, have an oxidation state equal to their charge. So something like Na+, that's a sodium ion that is not elemental sodium. So Na+ has an oxidation state of +1. Sodium neutral has an oxidation state of 0. Chlorine gas, Cl2, has an oxidation state of 0. Cl-1, the chloride ion, has an oxidation state of -1. Rule number 3 has to do with summing up the oxidation states of neutral compounds and polyatomic ions. If we sum up the oxidation states of all atoms in a neutral compound, we will get a total of 0. All right, so for something like sodium chloride, NaCl, we know it's a neutral compound because there's no charge up top. So if we sum up the oxidation state of sodium and chlorine, we will get a total of 0. Okay. We can use some of the other rules to figure out what the oxidation states of sodium and chlorine are, but it turns out that Na is +1 when it's part of a compound. Notice that it's not a free element in this state, it's part of a compound. The oxidation state of Na in a compound is +1. The oxidation of Cl in this case is -1. If we add the oxidation states of the sodium and the chlorine together, we get 0. The sum of the oxidation states of all atoms in a polyatomic ion is going to equal the charge on that ion. So in a neutral compound, when we summed up the oxidation states, we got a total of 0. For a polyatomic ion, when we sum up the oxidation states of each element in that polyatomic ion, we are going to get the same number as the charge on the polyatomic ion. So in this case, we're looking at nitrate. Nitrate has 1 nitrogen and it has 3 oxygens. When we sum up the oxidation state of all the elements in nitrate, we will get -1. And I will give you an example of that shortly. Rule number 4 has to do with group 1 and group 2 metals. All group 1 metals are going to have an oxidation state of +1 in the compounds that they form. Okay, so this is where we got that oxidation state for sodium previously, because sodium is a group 1 metal. All group 2 metals are going to have an oxidation state of +2 in all of their compounds that they form. So in this case, Mg would have an oxidation state of +2. Rule 5 has to deal with the rest of the elements that you're going to be looking at. Okay, any ones that have rules anyway. You're going to follow these rules in order that they're listed. So fluorine's oxidation state of -1 is more important than hydrogen's of +1. Hydrogen's oxidation state is more important than oxygen's. So anytime that 2 of these oxidation rules conflict, you defer to the one that came before. So let's look at this question. Which statement best describes the difference between the charge of the polyatomic ion and the oxidation states of its constituent atoms? Okay. If you take a second to read over these choices. We're talking about a polyatomic ion here in particular, not a monoatomic ion. So hopefully reading through these, it's clear that choice A is the correct one. The charge of a polyatomic ion is a property of the entire ion. The oxidation states are assigned to each individual atom. Okay. The oxidation state of the ion is the same as its charge. That does not make sense for a polyatomic ion because a polyatomic ion consists of many atoms. The charge of the polyatomic ion is not a real physical property. That's exact opposite. While oxidation states of atoms are, yeah, that's the reverse. Choice C is a reverse of the truth. Okay. Now we're going to use a whiteboard to run through how we assign oxidation states in polyatomic ions, and then how we use everything that we know to assign oxidation states to elements in compounds that have polyatomic ions in them. Okay? We're going to do this. We'll do these together, and then you guys can do the next set of slides on your own. Okay, let's start here with the phosphate ion, PO43 minus. So we know from our rules that when we have a polyatomic ion, the sum of each of the atoms that are in the polyatomic ion is going to equal the charge, the sum of each of the oxidation states of each of the atoms. I don't know if I said that whole sentence or not. So the sum of each oxidation state of each of the atoms in the polyatomic ion is going to equal the charge on the polyatomic ion. Okay, so whatever my oxidation state of phosphorus is, plus I have 4 oxygens, so I'm going to have to do 4 times the oxidation state of oxygen. When I add these values together, I should get -3. Okay. Now, from my list of rules, I can determine one out of 2 of these, right? I have a rule for oxygen. I don't have a rule for phosphorus, but I do know that according to that list of rules that I have, that the oxidation state of oxygen is -2 if no other rule contradicts that. Okay, so I don't know what my oxidation state of phosphorus is, so I'll leave that alone for now. But I do know that each of my oxygens is going to have an oxidation state of -2. Okay, and I have 4 of them, so I'm going to count each oxygen here. And when I add these values together, it's going to come out to -3. Okay, so my oxidation state of phosphorus, 4 times -2 is -8. That's going to equal -3. Let me add the 8 to the other side, and it turns out that the oxidation state of phosphorus in this polyatomic ion is +5. Okay, so if the question was, what is the oxidation state of each atom in this polyatomic ion, the oxidation state for phosphorus is +5, and the oxidation state of oxygen is -2, because we're looking for the oxidation state of each individual oxygen, not the total. Okay, I don't need to know what the oxidation state of 4 oxygens is. I need to know what the oxidation state of 1 oxygen is. All right, let's look at the next one. So this is the nitrite ion, NO2 minus. Okay, so very similarly to the last one, when we're comparing these two things, the rule for oxygen comes before the rule for any of our group 5s. So we're going to use the rule for oxygen to figure out what the oxidation state for nitrogen is. We know that when we add up the oxidation state of the nitrogen and the 2 oxygens, we're going to get a value of -1. So the oxidation state for nitrogen plus 2 times the oxidation state of oxygen is going to equal -1. The oxidation state of nitrogen plus 2 times -2 equals -1. Okay, I'd like to turn this into like a little algebra problem. I think it makes sense. 2 times -2 is -4. So the oxidation state of nitrogen in this case is +3. Okay. So that is how we find the oxidation states of atoms that are in polyatomic ions. All right, now let's look at how we figure out the oxidation states of atoms that are part of compounds that have polyatomic ions in them. Okay, so say I have something like this, Mg3 PO4 2. And I want to know what the oxidation state of everything in here is. All right. Now, I think it's easier to maybe separate out the polyatomic ion from the other ion in this case and do them one at a time. So I like to separate this out and say, well, I know that I have two phosphate ions here. And if we remember the process that we did before, we know that phosphate plus 4 times -2 is going to equal -3. And that phosphate's going to equal +5. Okay? That means that we know that every oxygen here is going to have an oxidation state of -2. Every phosphate's going to have an oxidation state of +5 because they're part of this polyatomic ion. We also know from our list of rules, and this you could have done before the phosphate end, because magnesium is a group 2 metal. That means that you know right away that magnesium is going to have an oxidation state of +2. You knew this before any of this other stuff. Now that we have all these numbers, we're going to check to see if they make sense, because if this is a neutral compound, which it is, then when we add up the oxidation state of everything that's present, we should get 0. So according to what I have down here, I have 3 magnesiums. Each magnesium has a +2 oxidation state. Now, I have 2 phosphate groups. That means I have 2 phosphoruses and I'm going to have 8 oxygens. So my oxidation state for phosphorus, I'm going to have to multiply by 2. And my oxidation state for oxygen, I'm going to have to multiply by 8. And when I add up all of these things, it should be 0. Okay? So 6 plus 10 minus 16 equals 0. 0 equals 0. We did good. Okay? Let's look at one more example. Okay, so again, right away, you know that this is going to be +2 because it's a group 2 metal, and that beats anything that's happening in here. Now, if we're focusing on when I split this up like this, just to be clear with you guys, I'm looking at the nitrite ion on its own before it was attached to calcium. And you don't actually have to do that. So let me try it. You know, I like to give you guys more than one way to look at things. So let's just go in order. My calcium is +2. I have 2 nitrites. That means that I have, we'll put a question mark by the nitrogen, because whatever is last on our list that we were given initially, that's what we're going to solve for in the end. So nitrogen is lowest on the list, or last on the list. So we're going to figure that one out last. We know that each oxygen has a -2 oxidation state. So we can solve it out this way. If you don't want to break it up into the ion form, you can look at it as just a neutral compound and figure out the oxidation state of your last remaining atom that way. So I've got 1 calcium, so that's going to be 1 times the oxidation state of +2. I've got 2 nitrogens, so that's 2 times whatever the oxidation state of nitrogen is. 2 times 2 is 4 oxygens, so that's 4 times -2. Because this is a neutral compound, they're going to equal 0. So 2 plus 2 nitrogen minus 8 equals 0. I'll combine these ones. So 2 times nitrogen minus 6 equals 0. So the oxidation state for nitrogen is +3, which we already kind of had an idea of because we solved for the nitrite ion by itself before. So in this case, I would say that my calcium has an oxidation state of +2. My nitrogen has an oxidation state of +3. And each of my oxygens has an oxidation state of -2. Okay. So now we have a whole list of them to try on the next slide. Okay, so here are a whole bunch of examples. And I would like you to pause this at this point and try to figure these out on your own. I'm going to go back to the whiteboard and sort them out. But it's really only going to be useful to you if you can do this on your own. Okay, so just looking at this list here, right off the bat, I am going to go to 2 that I see here from 1 to 10. This is an element, and chromium is an element. Anything that is a free element has an oxidation state of 0. So both of these have an oxidation state of 0. Okay, so right away, those are 2 giveaways. You have some other giveaways on here. Okay, because rule number 2 was anything that is a monoatomic ion is going to have the same oxidation state as the charge on it. So I've got 2 monoatomic ions here that I see, Na plus and Cr3 plus. That means that the oxidation state of sodium ion here is +1, and the oxidation state of chromium ion here is +3. All right. So now we will look at Kf. Out of these 2 atoms, potassium falls first on our list of oxidation state rules. It's a group 1 metal, so it has a +1 oxidation state. We know that the overall oxidation state of Kf has to be 0 when we add up the oxidation numbers of both components because it's neutral. That means that the oxidation state of fluorine has to be -1. Okay. For CO2, again, it's a neutral compound, so we know that when we add these things up, when we add the oxidation states up, it's going to equal 0. We also know that we have, between the 2 of these, we know the value of the oxidation state of oxygen. So we're going to have the oxidation state of carbon plus 2 times the oxidation state of oxygen, which is -2. When we add those together, we're going to get 0. So the oxidation state of carbon, 2 times -2 is -4 equals 0, +4, +4. So the oxidation state of carbon is +4. Okay, and the oxidation state of oxygen is -2. All right. Let's look at the next one. SO4 2 minus. This is a polyatomic ion. So now when we sum up the components of this polyatomic ion, the oxidation states of the components, we should get a -2. Between the sulfur and the oxygen, we're going to use the oxidation state of oxygen from our previous list as our starting point. And we will set it up like this. The oxidation state of sulfur plus 4 times the oxidation state of oxygen. I should use a big O there. Just make it O. That's going to equal -2. Okay. Oh, no, that's confusing also. So I'm going to just write oxygen up here, and I'm going to put the number here because it looked like a 0, so that looked weird. So 4 times the oxidation state of oxygen, which is -2. That looks better. So the oxidation state of sulfur, 4 times 2 is -8. That equals -2. Okay, so the oxidation state of sulfur is +6. And then the oxidation state of each oxygen is -2. Okay. Now we get really used to the oxidation state of oxygen being -2, and that can sometimes lead us astray. And that's especially true when you run into peroxides. So that's an example of what we're looking at right here. K2O2. Okay, because we have to remind ourselves that according to the list of our oxidation state list, that the oxidation state of potassium comes before the oxidation state of oxygen on that list. So we know that there's 2 potassiums and that each potassium, which is a group 1 metal, has to have an oxidation state of +1. Okay? We know that when we add the oxidation state of potassium to whatever the oxidation state of oxygen, when we add the oxidation state of potassium to 2 times the oxidation state of oxygen, that these things have to equal 0 because this is a neutral compound. Okay, so 2 times 1 is 2. We'll call this 2x just because that oxygen notation looks too much like a 0. So 2 plus 2x, when we add these things together, it has to equal 0. So I'm going to subtract 2 from both sides. 2x equals -2. X equals -1. And in this case, X, remember, was the oxidation state for oxygen. Okay, so here we see oxygen in one of its more rare forms where it has the oxidation state of -1 instead of -2. So in K2O2, each potassium has an oxidation state of +1. Each oxygen has an oxidation state of -1. CCl4, we have another neutral compound here. The chlorine is the first thing on our oxidation state list that we run into. And each chlorine has an oxidation state of -1. So the oxidation state of carbon plus 4 times the oxidation state of chlorine will equal 0 when we add them together. So when we solve for this, the oxidation state of carbon is +4. The oxidation state of each chlorine is -1. Okay, In this case, when we're comparing these two things, we're going to focus on the strontium first because it's a group 2 metal. Group 2 metals are all going to have an oxidation state of +2. So the oxidation state of strontium plus 2 times the oxidation state of bromine is going to equal 0. So 2 plus, we'll just call it 2x equals 0. 2x equals -2. X equals -1. And that is the oxidation state of the bromine. Okay, so strontium is +2, and each bromine is -1. Okay, number 11 is SO3. So the first oxidation number that we run into here is -2. Okay, so we're going to say the oxidation of sulfur plus 3 times the oxidation of oxygen is going to equal 0 because SO3 is a neutral compound. The oxidation state of sulfur -6 equals 0. The oxidation state of sulfur is +6. The oxidation state of oxygen is -2. All right, and our last example is the nitrate ion. We did the nitrate ion before, so now we can look at we did the nitrite ion before, now we can look at the nitrate ion. Each oxygen again is -2. So the oxidation state, so 1 times the oxidation state of nitrogen plus 3 times the oxidation state of oxygen is going to equal -1 in this case, because that is the charge on our nitrate ion. So the oxidation state of nitrogen -6 will equal -1. So the oxidation state of nitrogen is going to be +5 in the nitrate ion, and the oxidation state of oxygen will be -2. Okay. All right, so now when we go back, we can see all the answers there. Hopefully it makes sense to you how we got them. So now we're going to go one step further with this. We're going to use oxidation states to actually identify redox reactions, okay? Because when you look at a reaction like this, we have 5 examples here. You are going to be able to break down each of these reactions into the oxidation states of the components and decide whether you have a redox reaction or not. Okay, once you decide whether or not you have a redox reaction, you'll actually be able to tell what is being oxidized and what's being reduced just by looking at the oxidation states. So for each one of these, we will go through, let's see, I will demo, let me demo the first one for you on the whiteboard so we can look at this. We want to identify the element that is oxidized and the element that's reduced in the following reactions. Okay, so here's our reaction. Now the first thing that you need to do is you have to go through and assign oxidation states to every single atom that's in this reaction, step by step, just like what we just were doing, okay? So I like to start, just like I did with the previous example, I like to start with the things that are in their elemental form. I have elemental magnesium and I have elemental hydrogen in this balanced equation here. So right off the bat, I am going to say, well, the oxidation state of magnesium is 0. The oxidation state of hydrogen is 0, because that is elemental magnesium and elemental hydrogen. Now, for each of the other components, I'm going to have to do a little bit of work for each one, but then I'm going to be able to find the oxidation state. So if I have, you're going to notice also that I'm going to disregard this coefficient in front because the coefficients don't matter. You only have to look at the actual compound itself to figure out the oxidation state of the components in it. So if I have H2O, right, I know that each hydrogen is going to have a +1 oxidation state from my list of rules. There are 2 of them. That means that my oxidation state for oxygen has to be a -2. Okay, so I'm going to write that. Hydrogen is +1. I like to write my individual number up here for each atom. So even though the 2 hydrogens together have a total oxidation state of +2, I'm tracking the oxidation state of each individual hydrogen in this reaction. So each hydrogen on my reactant side has an oxidation state of +1. The oxygen has a -2. Okay? In my magnesium hydroxide over here, I can start off by saying that magnesium, which is my group 2 metal, will have a +2 oxidation state. Now, in my hydroxide part of this, right, I've got 2 hydrogens. Each hydrogen is going to have a +1. That means that let's keep track of my total positive oxidation state in this magnesium hydroxide. Let me do this down here so you're not doing it in your head. So we know that this is +2. We know that each hydrogen is going to be a +1. That means that magnesium plus 2 oxygens plus 2 hydrogens are going to equal 0, right? It's just like what we were doing before. It's just that in this case, we know that the hydrogen oxidation state is +1, and we know that the magnesium oxidation state is +2. So we have 2 plus 2 times oxygen plus 2 equals 0, or 2 times oxygen plus 4 equals 0. Okay, so 2 oxygens is going to be -4. Oxygen has an oxidation state of -2. We're not really that surprised by that, but you have to verify it every time just in case it's something special like a peroxide. So we can fill that in up here. Okay, now what you are looking for up in your equation up here, you're looking for changes in oxidation state. If you do not have any changes in any of the oxidation states in this reaction, then you do not have a redox reaction. Okay, so in this case, we do see some changes, so we're going to track them. Okay, let's look at what happened to magnesium. Magnesium went from an oxidation state of 0 to an oxidation state of +2. When we have an increase in oxidation state, that means that we have oxidation. That means that magnesium was oxidized. Okay, where else do we see a change? We see a change in the hydrogen. Hydrogen goes from a +1 to a 0. So a decrease in oxidation state means that we have reduction. Okay, so hydrogen, specifically your H2O, or your hydrogen in the H2O, was reduced. Okay, so now I want you to hit the pause button. For real, try all these other examples. Not everything here is a redox reaction. So it's going to be up to you to figure out whether you have a redox reaction or not, and then what is being oxidized and what is being reduced. Hit the pause button and try it out. And I am going to proceed with the explanation, but don't just let me explain it to you. Try it out on your own. This is how we learn. Okay, so over here now for number 2, you see that I'm going to start by assigning oxidation states to every component here. So my tin is going to be 0. I'm going to go through the process of assigning oxidation states to each of these components. Hydrogen will be a +1, nitrogen will be a +5, oxygen will be a -2. On the other side of this reaction, my tin is a +4, my oxygen's a -2. In NO2, my nitrogen's a +4, oxygen's -2. In H2O, my hydrogen's a +1, my oxygen's a -2. And I can see here that tin goes from a 0 to a +4. That's an increase in oxidation number, which indicates oxidation. Nitrogen goes from a +5 to a +4. That's a decrease in oxidation number. That is reduction. Okay. In my next example, I go through every one of these elements and I assign them all oxidation states. And then I'm looking between the reactant side and the product side here. And I notice that there is no change in any of the numbers. My mercury on this side and this side match. My nitrogen on the left side and the right side match. My potassium is matched. My oxygens match. My bromines match. Everything matches. There's no change in oxidation state. That means it is not a redox reaction. Okay? For number 4, my aluminum goes from 0 to a +3. My oxygen goes from a 0, because it's in its elemental form, to a -2. So my aluminum oxidation state increased. That's oxidation. My oxygen oxidation state decreased. That is reduction. Okay, and the last example here, I see again that I have no change in oxidation state in any of the components. This is another example of a non-redox reaction. So another term that we have, or 2 terms that we have to get familiar with, are oxidizing agents and reducing agents. Okay? Think about the definition of what an agent is. When we say something is an agent of something else, we mean that thing causes something, right? So I'm trying to think of like a good example, like, I don't know, I can't think of anything off the top of my head right now. But I mean, hopefully you know what I'm talking about here. An agent of something means that it's going to cause that thing. So a reducing agent is going to be something that causes reduction. An oxidizing agent means something that's going to cause oxidation. Well, what causes, like in terms of a reducing agent, what causes reduction? Reduction is caused by the oxidation of something else, right? If reduction means gaining electrons, where do those electrons come from? They come from an element that's oxidized, okay? So the reducing agent is going to contain whatever element has been oxidized. The opposite of that is the oxidizing agent. That's the thing that causes oxidation. Oxidation means a loss of electrons. So the thing that causes oxidation to happen is going to be the thing that takes the electrons away, or the thing that is reduced. So the oxidizing agent contains the element that is reduced. Now remember that these are coupled reactions. One is not going to happen without the other. So when reduction happens, it causes oxidation. When oxidation happens, it causes reduction, because when something loses electrons, they have to go somewhere. If something is going to gain electrons, those electrons have to come from somewhere, right? So your reducing agent will contain the element that is oxidized. Once that element is oxidized and it loses its electrons, It's going to cause the reduction of the other thing that's in the reaction. Okay, so let's look back at this example again with our sodium and our chlorine. We see here that sodium is oxidized and chlorine is reduced. If sodium is oxidized, that means that sodium is the reducing agent because sodium is causing the reduction of chlorine. Chlorine, on the other hand, is the oxidizing agent because it's causing the oxidation of sodium. Okay, notice that both of your agents are on the reactant side. So sodium is the reducing agent while it's being oxidized. Chlorine is the oxidizing agent while it is being reduced. Okay, so take a second to look at this. Which statement is true? Okay, so out of all of these, this is one that makes sense. In a redox reaction, any increase in the oxidation state of a reactant must be accompanied by a decrease in the oxidation state of another reactant. Because if electrons are being lost by one thing, they have to be being gained by another thing. Okay? Over here, this either or thing, that's what doesn't work here. They have to happen together. Oxygen is not necessary for it to be a redox reaction, and oxidation cannot occur independently of reduction. Okay, so now you have a nice, I'm not going to do all these for you, but I'll do a couple of them. You're going to determine whether each reaction is an oxidation reduction reaction. You're going to identify the oxidizing agent and the reducing agent of each one. Okay, so we'll start with the first one on the whiteboard. Okay, so I'm going to start by labeling the oxidation state of everything that's here. My magnesium is in its elemental form, so it has an oxidation state of 0. My oxygen here is in its elemental form, so it has an oxidation state of 0. In this compound here, MgO solid, my magnesium will have an oxidation state of +2. My oxygen will have an oxidation state of -2. All right, so now we can see very easily that the magnesium is oxidized. And the oxygen is reduced. If the magnesium is oxidized, that means that it is the reducing agent. If O is reduced, that means it is the oxidizing agent. Okay. All right, here's the next example. We're going to go through and label the oxidation states first. For HBr, hydrogen will be +1, Br will be -1, calcium will be +2, hydrogen will be +1, oxygen will be -2. You should do that, break that up if you're still having trouble with that, okay? And write out all of the pieces until you get those values. For H2O, each hydrogen will be +1, oxygen will be -2, calcium will be +2, Br will be -1. And notice again that when I'm writing up these oxidation states, that they're for the individual atoms, right? So this +1 here, for example, for the hydrogen, it's for each hydrogen, okay? Each hydrogen has an oxidation state of +1. Now the most important thing is looking at this, noticing that I do not have any change in the oxidation state of anything from the reactant side to the product side. So this is not a redox reaction. Okay, there is no reducing agent or oxidizing agent because it's not a redox reaction. Okay, let's look at one more example together. Again, I'm going to start this by assigning oxidation states to everything. And I always like to start with my atoms that are in elemental form and giving them an oxidation state of 0. Next, I'm going to look at my two other components here. They are both monoatomic ions. So they are each going to have the oxidation state of the charge of the ion. Once I have my oxidation states labeled, then I can look here and I can say that my zinc is oxidized because the oxidation number is increasing. If zinc is oxidized, that means that it's a reducing agent. Okay, my iron goes from Fe2 plus, or goes from +2 rather to 0. So that is being reduced. If iron is reduced, then it is the oxidizing agent. Okay, let's look at the other answers and you guys can compare them to what you did. Okay, so here are our next two. We see here for number 4 that lithium is oxidized. It goes from an oxidation state of 0 to +1. That's oxidation, so it's the reducing agent. Chlorine goes from 0 to -1. That's reduction, so chlorine is the oxidizing agent. Example number 5, aluminum goes from 0 to +3. So aluminum is oxidized, it's the reducing agent. Tin goes from +2 to 0, so its oxidation state is decreasing, so it's reduced. It's the oxidizing agent. For number 6, if you write out the oxidation states for each of the components here, you'll find that there is no change in oxidation state. That means that it is not a redox reaction. For number 7, carbon goes from 0 to +4. That's oxidation. That means that carbon is the reducing agent. Oxygen goes from 0 to -2, so it's reduced. That means that oxygen rather is the oxidizing agent. Okay, so that sums up oxidation and reduction. The last thing that we have to talk about very briefly is the activity series. And the activity series is a way to gauge how reactive different elements are when compared to other elements, okay? So the activity series is a list of the elements, and they're listed from most reactive up on the top of the list to least reactive on the bottom of the list. And this is what that will look like. Okay, so lithium up here is the most reactive, and it's most reactive because it's most easily oxidized, which means it's very easy for lithium to give this electron up. Okay, if it's easy for lithium to give the electron up, that means that it's going to react with things more readily than something at the bottom of the list. Okay, you should be able to look at an activity series and figure out from that series what is more reactive than something else. But you don't have to memorize the order of the series, okay? But you should be able to look at something like this and figure out the answer. Which metal here is most easily oxidized? We have sodium, chromium, and gold. So let's look back at this list. We have sodium up here. We have chromium in the middle. We have gold at the bottom. All right, well, things that are most easily oxidized are up at the top. That means that sodium metal is going to be the most easily oxidized out of those 3 choices. Okay, so hopefully that makes sense to you guys. Keep doing the practice problems and email me if you have any questions.